Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today, we're diving into a paper published December 6, 2024, titled Wavelet Diffusion Neural Operator. Alright, so this work tackles the challenge of simulating complex physical systems, things described by partial differential equations. The researchers propose a new framework called WDNO. It uses diffusion models, but cleverly applies them in the wavelet domain. This helps handle sudden changes in the system. They also introduce multi-resolution training to make it better at generalizing across different scales. It looks quite promising for both simulation and control tasks. Okay, and for those interested in trying this out themselves, the authors have actually made their code publicly available. So what we're looking at here is a snapshot of their GitHub repository. You can see the code structure on the left, folders for different experiments like Berger's equation and smoke simulation. And on the right, the README file gives you instructions, environment setup, links to download datasets and pre-trained checkpoints, and even the specific commands to run for training and inference. It's great to see this level of openness. Really helps others build on their work. Okay, so this figure gives a nice visual overview of the whole WDNO framework we've been talking about. It shows both the training and the inference processes. You can see how the data starts in the original domain, gets transformed into the wavelet domain, then goes through the core diffusion process, which involves adding noise for training or denoising for inference. Finally, it's transformed back to the original domain. What's really neat here is how it shows the two key components working together. The base resolution model, or BRM on top, handling the standard resolution, and the super resolution model, or SRM below, which is trained on downsampled data, but then used during inference to actually upscale the output, giving that zero-shot super resolution capability they mentioned. It visually lays out that multi-resolution strategy. Alright, so building on that framework, this table shows us the actual simulation results. It compares WDNO against several other methods on different fluid dynamics problems, both 1D and 2D, plus the ERA5 real-world dataset. Lower numbers here mean better accuracy, and as you can see, WDNO, our method, shown in the bottom row, consistently gets the best or very close to the best results, highlighted in bold. For instance, on 1D Navier-Stokes, its error is more than 2 times lower than the standard diffusion model DDPM. And on the 2D fluid task, it's an order of magnitude better. This really backs up their claims about performance. Alright, so moving from the quantitative results in the table. Figure 2 gives us some qualitative visualizations. On the left, we see the 1D Navier-Stokes results again. The dashed black line is the true state. The purple line is WDNO, and the pink line is the standard diffusion model DDPM. You can really see how WDNO captures those sharp jumps, the shock waves, much better than DDPM does, which aligns with the lower error we saw in the table. Then on the right, we see the 2D control task in action. The goal is to steer that yellow smoke around the gray obstacles to reach the target area at the top. These snapshots show how WDNO controls the flow over time, successfully guiding the smoke through the maze. It's a good visual demonstration of its effectiveness in a more complex control scenario. Okay, so shifting gears slightly from the visualizations. Table 2 here gives us quantitative results, specifically for the control tasks. This part, Part A, focuses on the 1D Berger's equation control problem. The column J represents the objective cost, so lower is better, meaning the control was more effective. And again, we see WDNO at the bottom achieving the best score, 0.0205. That's lower than the next best method, SL, which got 0.0235, and also better than the standard diffusion model DDPM at 0.0272. So, just like in the simulation tasks, WDNO shows superior performance here, finding more optimal control solutions for this system. And now, looking at the second part of Table 2, this shows results for a much more complex 2D fluid control task. Remember that smoke steering problem we saw visualized earlier? Well, here's the quantitative measure. Again, J is the cost. Lower means better control. Wow, look at WDNO's score here, 0.0679. Compare that to the other methods like BC, BPPO, and even the standard DDPM, which are all clustered around 0.3 or higher. WDNO is significantly better, achieving a much lower cost. This really demonstrates its advantage in handling these challenging high-dimensional control problems, finding much more effective solutions than the baselines. Okay, and speaking of capabilities, Figure 3 here demonstrates that zero-shot super resolution we talked about earlier, specifically for a 1D problem. The columns show different levels of upsampling: none, single, and double. Alright, the top row is WDNO's output. The middle row is the actual ground truth, and the bottom row shows the difference or error. So, what you can see is, as we move to higher resolutions, going from left to right, the WDNO prediction in the top row gets visually closer to the ground truth in the middle row. And importantly, the error shown in the bottom row gets smaller, indicated by the darker colors. This really highlights how the model generalizes to finer resolutions it wasn't explicitly trained on. Okay, so building on that visual demonstration from Figure 3, Figure 4 here gives us the quantitative results for that zero-shot super resolution. What we're seeing are plots of the log mean squared error. So lower is better against the number of upsampling steps performed. Alright, across the plots for both 1D, that's plot A, and 2D, plot B, you can see WDNO. The purple line consistently achieves lower error as the resolution increases compared to other methods like FNO and WNO, and plot C shows it compared to DDPM. Again, WDNO maintains a lower error, especially after multiple upsampling steps. This really backs up quantitatively what we saw visually. The model effectively generalizes to higher resolutions. Okay, so those quantitative results really drive home the effectiveness of this wavelet diffusion neural operator. The key takeaway is really its impressive ability using that wavelet and diffusion combination to generalize and perform zero-shot super resolution for complex systems like PDEs better than previous approaches. This matters because efficiently solving these equations is crucial for accelerating scientific discovery and engineering simulations. Alright, that's all for this episode. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.